All right, we're back. We're working on goodness of fit problems, and next we're going to do a practice problem, uh, looking at a goodness of fit test for a chi-square test of independence. This question, 13 from chapter 12 of your book. I'll read it aloud and then we'll work through it. Again, this is going to be a little bit different. I'm going to show you how to work it through in Excel. Get a new sheet up for us. With double-digit annual percentage increases in the cost of health insurance, more and more workers are likely to lack health insurance coverage. That's from a USA Today story in 2004. The following sample data provide a comparison of workers with and without health insurance coverage for small, medium, and large companies. For the purposes of this study, we're defining small companies as companies with fewer than 100 employees, medium companies with between 100 and 99 employees, and then large is going to be larger than that. We have sample data for 50 employees of small companies, 75 employees of medium companies, and 100 employees of large companies. And then we're given this contingency table. Part A is asking us to conduct a test of independence to determine whether the employee health insurance coverage is independent of the size of the company. It gives it a level of significance of 5% and wants to know what our conclusion is. So, what is the p-value? What is our conclusion? Well, first, we can't have a p-value until we have hypotheses. So, let's put together our hypotheses. For tests of independence, our null is always that they are independent. Right? So we can state the two characteristics. One is health insurance coverage, so we're saying that health insurance coverage is independent of firm size. The alternative is that they're not independent. As simple as that. You just state the two categories, and that's what you got. Step 2, again, is easy. They give us alpha equals 0.05 right here, so that's what we're going to use. For independence tests, we always use this. I used rows and columns as R and C. Now we're using rows and columns as I and J. The index doesn't matter. Ultimately, what we're going to do is for every observation, for every cell that we have here, we have an observed frequency, right? The observed number of people who, or number of people who worked for small companies and said yes was 36. So that's going to be F11. That's our observed frequency. Then we're going to have an expected frequency we have to construct. We're going to take the difference, square it, and weight it, divided by EIJ. And once we do that to all of the observation, or all of the cells, all the categories, we're going to add those up. When we do that, we're going to get a chi-squared test statistic. Under the null, it has a chi-squared distribution where n is the row number of categories and m is the column number of categories. It doesn't really matter which one you refer to as row and column. It's just going to be the number of categories in one direction minus 1 times the number of categories in the other direction minus 1, and that will be the degrees of freedom that we use. Okay, so that's the test statistic. In order to do this, we're going to need to build a contingency table, an expected contingency table, and then we're going to need to pull the information out of those to get to the what's the word I'm looking for? Oh, the goodness of fit table that we traditionally use to solve this sort of a problem. Add another parenthesis here, just typo. Okay, so our expected frequencies, in every case, it's going to be the row total times the column total divided by a sample size. This is what it's going to end up looking like, but first I want to show you how we find it with Excel. Easy way to find it with Excel. So let's pull up that thing that I put together here. I just copied and pasted the table. So this is I'm going to put observed here so that I don't get it confused. We have an observed contingency table. And all you see there is observed, but that's fine. That's plenty of information. And we have a total in one direction already that the question gave us. We're going to want to come up with a total in the other direction. So I'm going to use the sum function to calculate. Turns out we have 189 respondents said yes, they have health insurance, and 36 said no. Now you should notice that if we add these up, we get 225 in this direction. If we add these up, we get 225 in this direction. Doesn't matter which way you go. I'm going to go this way because I can just copy and paste, but we're going to want to have the total. That's n, right? Okay, now what we want to do is we're going to want to create an expected contingency table. It's going to look similar. We're going to have health insurance here with and size of company here. Small, medium, large, yes, no, total. Oh, I forgot total over here. Whoops-a-daisy. Okay, now, if you remember, let's look back at this formula here. So for row 1 and column 1, which is going to be E11, it's going to be the row 1 total times the column 1 total divided by the sample size. The row 1 total is 50, the column 1 total is 189, and the sample size is 225. So we can either do this as equals 50 times 189 divided by 225. That'll give us the right answer, 42. But what I'm going to do is I'm going to use cell references so that I can make this simpler. This is going to be equals 50 times 189 divided by 225. Okay, now if I try to just copy and paste this, I get an error. The reason is that it moved all the cells over. Now, what I wanted to do is I wanted to move the column cell over, the column total over, because I'm now in column 2, but I don't want to move the row. So I can use absolute positioning to fix that. So for whenever you put a dollar sign in front of something, Excel doesn't change it. So I know that I always want to deal with for my row total, it's always going to come from column D. So I'm going to put a dollar sign in there so the D doesn't change. Now for my column totals, they're always going to come from row 6. So I'll put a dollar there. And for my sample size, it's always going to be in exactly the same place. It's always in D6, so I don't want to change that at all. So now when I copy and paste this, it gives me the right answer, right? It moves the row. Now I'm looking at 36 or 50 times 36 divided by 225. That's correct. That's what I want it to be. I can double check, make sure that these stay the same. They should. That's still 50. Now when I copy and paste this down, you can see that the row has shifted, but the column has stayed the same. So now I'm doing 75 times 189 divided by 225. You can see that it's the blue times the green divided by the purple, which is good. That's what I want it to be. I can copy and paste this again here, and then paste it, and then I can copy and paste my totals. Oops. And then I want to sum these to make sure that it works for the rows or the columns. And sure enough, my totals should be exactly the same. And you can see that my totals are the same as they were here. Right, this matches with this, and this matches with this. What's different is the inside. Right, we've just moved stuff around a little bit so that in this case they're not independent ultimately. But using the formula, what we've done is we've generated a group of things that are independent. You can see actually that if you take this, divide the proportions, turns out that this is going to be the same as this. 22% of everybody works for small companies. 22% of people who have health insurance work for small companies. 22% of people who don't have health insurance work for small companies. And that's what independence just tries to do. It equalizes the proportion so that they're independent. Okay, well now we have our two tables. Now this is becoming a problem like the one that we've dealt with before, because now we have, if these are going to be our FIs and these are going to be our EIs. It takes a little while to build this contingency table, but once we have it, we're in good shape. You can see here I calculated this before, and this is what I got. Next, we're going to turn this into a goodness of fit type table. It's going to look like this when we're done, but the way that we do this is we take our categories, our rows and our columns, and we put them together. So we have size, and health insurance. And we have small yes, small no, medium yes, medium no, large yes, and large no. And those are all the combinations for our goodness of fit table. Now we're going to be building our FIs and our EIs. We actually already figured these out, right? Our FIs just come from here, our observed frequencies. Small yes is 36, small no is 14, medium yes is 65, medium no is 10, large yes is 88, and large no is 12. They gave us, the question gives us that stuff. For EI, this comes from the contingency table we built, and this is where a lot of the heavy lifting is in this type of problem. 42 people, if independence were totally the case, if these were perfectly independent within our sample, we'd have 42 people who worked for small companies would say yes, 8 people would say no. 63 medium yeses, 12 medium no's, 84 large yeses, and 16 large no's. So now the next thing is to find the deviations from our expectation. So Fi minus EI is going to be our deviation. Fi minus EI, and then once we've done that once, we can copy and paste it. And with independence, you often have something that looks kind of nice and parallel like this, especially when you only have two categories in one dimension. Then you're going to get offsetting entries like this. And again, in every case, when you add these up, the sum should be 0. So if you're not sure if you've done it correctly, that's how it should be. On average, we match our expectations. Now we're going to square this. So we take this and raise it to the second power. You can do this by hand if you want. Again, since I have the power, it's one of the really nice things about using Excel is that the formula is right there. So if I did it wrong, I can see what I did wrong. It's not a mystery as to where the number came from. I can just look at the formula I used. All right, so once we've done that, we need to weight it by dividing by the expectation. So we take this and divide it by, we take column K and divide it by column I. I'm just pressing Control D, which just fills it down. It just takes whatever's above it and drops it down one. So you can see in every case it adjusts. If you look up here at the formula, you can see as I scroll down, it's adjusting the row that it's taking care of. All right, now we want to get our chi-squared. We just need to add all these up. Once we get to this column, we should be fine. 6.94 is our chi-squared. I can write that here just so I know what I have here. Chi-squared is 6.94. And how many degrees of freedom do we have? Well, it's going to be the number of categories in one dimension, which is 1, 2, 3, minus 1, which is 2. So we have, let's do row categories, 3, column categories, 3 and 2. Subtract 1, and then multiply them together. 2 times 1 is 1. We're going to have 2 degrees of freedom. So chi-squared with 2 degrees of freedom. And 6.94 is our test statistic. So let's go back here. You can see, yep, this is what your table should look like. Something like this when you're in good shape. And we can draw conclusions now. Now, chi-squared, normally with chi-squared it looks something like this. And so if you did it like this, that's totally fine. In this case, when you have very low degrees of freedom, it actually looks kind of like this. So this is an actual scenario where I used Excel to generate the function. But using the drawing just like that is perfectly fine. We do have our test statistic, so we can put that, you would want to put that here. And because this is a goodness of fit test, that's a 4. It's always going to be an upper tail test. So what do we have in the upper tail? Well, if you're looking on the chi-squared chart, you can see we have 2 degrees of freedom. We go all the way across. 6.94 was our test statistic, and it's going to fall in here somewhere in between 5.991 and 7.378. It means our area in the upper tail is going to be greater than 2.5% and less than 5%. So going back here, we can see, yep, that's where this is. And that's going to be our p-value. It falls right there between 0.025 and 0.05. That is less than alpha. That's our p-value. And whenever the p-value is less than alpha, we reject the null. So that's the conclusion we come to. We can reject the null. These two do not appear to be independent. I'm not going to finish part B. I'm going to leave that to you guys. You can figure out what the percentages are to figure out who's most likely. It looks like small companies are more likely to be uncovered by insurance. So there's that. All right, I hope that was helpful. If you have any questions, please shoot me an email at jjdelaney@ualr.edu or leave a comment, and I will be in touch. Thanks, and I'll talk to you soon. Bye.